Modern commercial aviation operates on a fundamental mechanical compromise, relying on engine compressor stages to provide life support and thermal regulation for the pressure vessel. This pneumatic umbilical cord, known as bleed air, extracts pressurized atmospheric gas from the engine core before combustion occurs, routing it throughout the entire airframe. While historically reliable, this architecture contains a critical vulnerability, directly linking the aircraft's internal atmospheric conditions to the catastrophic mechanical failures of the propulsion system. When high-bypass turbofans suffer severe dynamic trauma, such as massive bird strikes or fan blade separation, kinetic imbalances threaten to tear the engine from the wing. To prevent structural failure, modern engines utilize a load reduction device, intentionally decoupling the fan section from the core machinery to mitigate catastrophic vibrational energy. This mechanical decoupling violently shears internal fluid lines, instantly releasing gallons of synthetic lubricating oil directly into the extreme thermal environment of the compressor stages. Operating at temperatures exceeding 200 degrees Celsius, the compressor instantly vaporizes this synthetic oil, transforming it into a dense, highly toxic, acrid white smoke. Because the traditional pneumatic architecture draws directly from these contaminated compressor stages, the vaporized oil is immediately pumped through the environmental control systems. Within seconds, the passenger cabin and the flight deck are completely inundated with toxic smoke, creating an immediate and severe physiological hazard for all occupants. This catastrophic atmospheric contamination typically occurs at low altitudes during takeoff or landing, exponentially increasing the cognitive load on the flight crew during critical phases. While digital software patches attempt to automate the closure of bleed valves upon detecting severe vibrational anomalies, these remain reactive measures to a systemic architectural flaw. The aerospace industry has tolerated this pneumatic vulnerability for decades, simply because extracting kinetic energy directly from the compressor was the lightest, most efficient solution available. Early jetliners required a reliable mechanism to pressurize the cabin, de-ice the leading edges, and actuate heavy mechanical systems without relying on primitive electrical grids. Bleed air provided massive amounts of raw kinetic energy, allowing engineers to bypass heavy electrical generators and utilize the existing thermodynamic output of the turbofans. However, this energy extraction exacts a heavy toll, siphoning compressed air away from the combustion chamber and measurably degrading the overall thrust efficiency of the engine. Furthermore, harnessing this extreme thermal energy requires a massive logistical footprint of heavily insulated titanium ducting, high-pressure valves, and continuous leak detection sensor networks. Every pneumatic junction represents a potential point of catastrophic failure, where escaping superheated air can melt critical wiring harnesses or compromise the structural integrity of the wing. The economic penalty of this architecture is severe, demanding continuous physical inspections and driving up long-term maintenance costs across the life cycle of the airframe. As global energy markets contracted and fuel efficiency became the supreme metric of aerospace survival, the mechanical drag of pneumatic bleed systems became an unacceptable operational liability. In the early 21st century, the Boeing Corporation initiated a radical architectural divergence, designing an airframe that fundamentally severed the traditional pneumatic umbilical cord entirely. The Boeing 787 Dreamliner was engineered with a cold, calculated objective: eliminate the bleed air infrastructure and replace it with a massive, redundant electrical power grid. By eliminating the pneumatic connection between the engine core and the pressure vessel, the 787 achieved absolute immunity from compressor-induced cabin smoke contamination events. Instead of stealing compressed air from the engines, the 787 utilizes dedicated external fuselage inlets to draw clean atmospheric air directly into massive electric compressors. These solid-state electrical compressors pressurize the cabin independently, routing clean air through localized environmental control packs without any physical exposure to internal engine lubricants. To achieve this independence, Boeing mounted two massively scaled electrical generator motors directly to the accessory gearbox of each turbofan engine, generating unprecedented electrical output. Combined with two additional generators on the auxiliary power unit, the 787 architecture is capable of producing 1.4 megawatts of raw electrical power. This staggering electrical capacity is enough to power an entire neighborhood, fundamentally shifting the energy distribution paradigm of the aircraft, from pneumatic to purely electromagnetic. The elimination of hot pneumatic ducting also revolutionized the thermal management of the airframe, replacing complex bleed valves with embedded electrical heating matrices in the wings. These localized heating elements provide granular, precision-controlled de-icing capabilities, targeting specific aerodynamic surfaces only when required and eliminating ambient thermal waste entirely. Furthermore, the transition to high-voltage electrical architecture allowed Boeing to eliminate volatile hydraulic braking systems, utilizing electric actuators to apply massive stopping force to the landing gear. However, this radical electrical paradigm shift required doubling the baseline voltage of the aircraft from 115 volts to 235 volts of alternating current. Managing this immense electrical load requires sophisticated, solid-state power conversion systems and highly complex automated control logic to dynamically prioritize critical flight systems. In executing this design, Boeing effectively traded the mechanical complexity of high-temperature pneumatic plumbing for the digital complexity of advanced power electronics and heavy electrical cabling. The strategic calculation was clear. The aerodynamic and thermal efficiency gains of a bleedless engine would offset the immense weight penalty of the new electrical generators. Boeing engineers projected a structural fuel burn reduction of up to 3%, a massive strategic advantage in the highly competitive long-haul commercial aviation sector. Yet, when Airbus began developing the competing A350 program, their strategic analysis of the bleedless architecture yielded a starkly different and highly conservative conclusion. Airbus engineers determined that the net energy extraction penalty remains constant, regardless of whether the power is extracted pneumatically through air or mechanically through electrical generators. Their systemic analysis revealed that the immense weight of the redundant generators, heavy copper cabling, and required thermal cooling systems negated the promised efficiency gains. The A350 program was already attempting to integrate a revolutionary composite fuselage manufacturing process and the most powerful civil turbofan engines ever designed by Rolls-Royce. Introducing an unproven, high-voltage electrical architecture on top of these existing variables was deemed an unacceptable programmatic risk with severe implications for global certification schedules. Consequently, Airbus retained the traditional bleed air architecture, utilizing advanced miniaturization and highly optimized thermodynamic materials to mitigate the historical inefficiencies of pneumatic systems. They specifically avoided the highly volatile lithium-ion battery architecture that would later plague the 787 program with catastrophic thermal runaway events during its early operational deployment. Instead, Airbus deployed a strategy of selective electrification, targeting highly localized hydraulic and flight control systems where solid-state actuators provided the maximum tactical advantage. The Rolls-Royce Trent XWB engine was custom-calibrated to synchronize perfectly with the A350's pneumatic network, achieving thermal efficiencies that rivaled Boeing's radically unproven electrical gamble. The strategic divergence between Boeing and Airbus highlights a fundamental geopolitical reality. Technological supremacy is rarely absolute, and competing architectures often achieve identical operational parameters. The 787 proved that severing the pneumatic umbilical cord is technologically viable, establishing a new baseline for how energy is managed within complex aerospace platforms. Conversely, the A350 demonstrated that aggressive refinement of legacy mechanical systems can match the performance of radical innovation without incurring catastrophic developmental risks or delays. The future of aerospace engineering is now shifting toward micro-hybridization, combining the thermal resilience of pneumatic systems with the granular precision of advanced electrical matrices. As global mandates force the exploration of alternative propulsion vectors like hydrogen fuel cells, the extreme electrical architecture pioneered by Boeing will become increasingly critical. Ultimately, the threat of toxic cabin smoke remains a physical constraint of legacy designs, forcing the industry to continuously balance passenger safety against the realities of mechanical engineering. The strategic persistence of pneumatic systems in the Airbus fleet is not merely a refusal of progress, but a calculated bet on the reliability of established physical laws. By optimizing the bleed air architecture, engineers have reduced the thermal signature and pressure loss within the ducts to levels previously thought impossible for conventional designs. This optimization involves the use of adaptive control valves that modulate airflow with millisecond precision, ensuring the engine core only surrenders the exact volume of air required. However, even the most refined pneumatic system cannot bypass the fundamental chemistry of synthetic engine oil when it encounters a 1,000-degree turbine environment. The structural reality remains. As long as the cabin air supply is physically shared with the engine's internal compression path, the risk of aerosolized toxicity persists. Boeing's 787 remains the sole outlier in this global fleet, having successfully insulated its passengers within a closed-loop atmospheric bubble, completely independent of the propulsion cores. This atmospheric insulation is achieved through 4 high-performance, electrically driven compressors located in the aircraft's cheek areas, far removed from any potential oil leakage zones. These units are the heartbeat of the Dreamliner's life support system, drawing ambient air from dedicated scoops and filtering it through high-efficiency particulate and gas phase scrubbers. The transition to this more electric aircraft, or MEA philosophy, has forced a total redesign of the engine's power takeoff architecture and the aircraft's thermal management. Without hot bleed air to drive the air conditioning packs, the 787 must manage the massive heat rejection generated by its own high-output electrical power electronics and converters. This necessitates an intricate liquid cooling system, utilizing a network of heat exchangers and ram air scoops to prevent the solid-state power components from reaching critical failure temperatures. In contrast, the Airbus A350 utilizes its pneumatic bleed air to naturally regulate the temperature of its systems, essentially using the air as both a power source and a coolant. This traditional approach avoids the weight and complexity of secondary liquid cooling loops, reinforcing Airbus's claim that pneumatic systems offer superior power-to-weight ratios for specific missions. The debate between Boeing and Airbus isn't just about engineering. It is a battle over the future of aircraft maintenance and the mean time between failures metric. Electrical systems are inherently easier to monitor via digital diagnostic tools, allowing for predictive maintenance that can identify a degrading generator before it fails mid-flight. Pneumatic systems, however, are notorious for ghost leaks, pinhole fractures in titanium ducting that are nearly impossible to detect visually until they trigger a localized overheat alarm. For airlines, a bleed air failure often means an immediate diversion to the nearest airport, as the loss of cabin pressurization is a non-negotiable safety violation. By shifting to an all-electric architecture, the 787 provides multiple layers of redundancy, where a single generator failure has zero impact on the cabin's atmospheric integrity. Yet, the early years of the 787 program demonstrated that electrical complexity carries its own set of black swan risks, specifically regarding high-energy density storage. The 2013 grounding of the entire global Dreamliner fleet, due to battery fires, served as a stark warning to the industry about the volatility of rapid electrification. These thermal runaway events were the physical manifestation of pushed limits, where the demand for massive electrical current exceeded the safety margins of the existing battery chemistry. While Boeing eventually resolved these issues through reinforced stainless steel containment boxes, the incident vindicated Airbus's more cautious, incremental approach to the A350's design. Airbus effectively leveraged the 787's growing pains to market the A350 as a more mature and stable platform for conservative airline operators worldwide. This brings us back to the central problem of cockpit smoke. If the solution is obvious, the bleedless architecture, why hasn't it become the global regulatory mandate? The answer lies in the brutal economics of aircraft certification and the multi-decade life cycles of the narrow-body workhorses like the 737 and the A320. Retrofitting an existing narrow-body airframe with a bleedless system would require a total structural redesign of the wings, the fuselage, and the engine mounting pylons. The cost of such a redesign would be measured in billions of dollars, making it financially impossible for manufacturers to implement on anything other than a clean sheet design. Consequently, pilots flying the 737 MAX or the A320neo must continue to rely on software-based mitigations and emergency procedures to handle potential oil ingestion events. These software patches, while sophisticated, are fundamentally band-aids placed over an architectural bypass that was designed in an era of lower safety expectations. In a power narrative view, the airframe is a system of constraints where every safety improvement must be bought with a corresponding sacrifice in weight or range. To eliminate smoke events entirely on the narrow-body fleet, airlines would have to accept significantly higher ticket prices to offset the massive capital investment of new fleets. This creates a strategic stalemate, where the industry accepts a statistically insignificant risk of smoke events, rather than upsetting the global economic equilibrium of flight. But as the world moves toward decarbonization, the pressure to electrify everything is no longer just about safety, it is about the survival of the aviation industry. Future zero-emission aircraft, whether powered by hydrogen fuel cells or solid-state batteries, will by necessity be entirely bleedless in their design architecture. Hydrogen fuel cells produce electricity directly, meaning there is no compressor to bleed air from, necessitating a 787-style atmospheric control system for all future long-haul craft. Boeing's gamble with the Dreamliner may have been painful in the short term, but it has positioned them as the primary architect of the post-carbon flight paradigm. They have already solved the complex challenges of high-voltage power distribution and large-scale electric compression that Airbus is only now beginning to explore. Airbus's Zero project is currently testing hydrogen combustion engines, which may still utilize modified bleed systems, showing their persistent reluctance to abandon pneumatic logic. This technical friction between more electric and optimized pneumatic will define the geopolitical competition between the American and European aerospace sectors for the next 50 years. The winner will be the entity that can provide absolute atmospheric safety zero smoke risk without compromising the hyper-efficiency required by a carbon-taxed world. In the cockpit of a 737 MAX today, the pilot still monitors the bleed air temperature gauges, a relic of 1960s mechanical philosophy in a 2020s digital world. When a bird strike occurs, that pilot has only seconds to recognize the olfactory signature of vaporized oil before the cabin environment becomes untenable for human life. The physical reality of the flight deck during a smoke event is one of extreme sensory deprivation, where vision is obscured and communication is hampered by oxygen masks. Every second spent running a smoke removal checklist is a second taken away from the critical task of navigating a crippled aircraft back to the runway. System-level logic dictates that the most effective way to manage a crisis is to eliminate the physical mechanism that allows the crisis to manifest in the first place. By decoupling the air we breathe from the engines that propel us, we move from reactive emergency management to proactive structural safety and environmental resilience. The Boeing 787 is not just a better airplane, it is a manifestation of a new philosophy that views the aircraft as a holistic, integrated electrical organism. As we look toward the 2030s, the bleed air era is slowly entering its twilight, victim to the relentless march of electrification and the non-negotiable demand for air purity. The obvious solution was never ignored. It was simply waiting for the electrical technology to catch up to the lethal physics of high-speed turbine flight. The transition is inevitable, but until then, the safety of millions remains tied to the integrity of a few titanium pipes and the vigilance of the flight crew.